Hi, Bob. May we please have a drink of water, Uncle Bob?
You certainly may. That's one thing I have plenty of. Help yourself.
Boy. I'm next.
Plenty for everybody.
I'm next.
Well, what's this, the seventh inning stretch?
No, we are just practicing. Morning water sure tastes good. Boy, nothing like water when you're thirsty.
Oh, you're so right, Mike. You know, man can add all sorts of things to water to make it taste differently and have pretty colors. But when you're really thirsty, boy, you'll choose just plain old water. Say, by the way, do you fellas know what water's made of?
What do you mean, made of? You mean water's made out of something else?
It is that. What do you think water is?
I always thought water was just water. Yeah, just plain H2O.
Ah, there you are, Ted. Okay, now what do you mean by just H2O?
I don't know. I guess it's sort of a nickname for water, isn't it?
I guess H2O has become sort of a slang expression meaning water. But actually, H2O is the chemical formula for water. But why do we use the letters H and O with a little 2 in the middle?
I don't know. Tell us, Uncle Bob.
All right, I will. Come on into my lab for a few seconds and we'll do some detective work and solve the mystery of why we call this H2O.
And he's going to teach those boys the wonders of H2O, or what we call water. And we're going to do the same thing tonight. Now, we are in these, every week we have a different lecture, and usually we're looking into the Word of God more distinctly, but every once in a while we look at these subjects of nature. And there's a reason behind that. In Romans chapter 1, and verse 20, the Apostle Paul said, "For the invisible things of him, that is God, from the creation of the world, are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they, or people, are without excuse." And so there's this another book, it's called the Book of Nature, which God has given unto man, that all men have to look around them and see the handiwork of their Creator and to recognize it. And it's very important for us to do that. If you haven't yet believed in God or accepted him, it's very important to see in his creation this intelligent design that is there. If you are a believer, I think it's even equally important that we always go back and we just stand in awe at the things that God has made. When we consider the work of his fingers, the moon and the stars and the heavens that he has made, it makes us wonder, who are we? What is man that thou art even mindful of him? And so that's often what we do, right? You often look up into the stars and you get this sense of awe that comes over you, which is very important. And it makes us humble, and it realizes that there is a creator. But there are these signs all around us, and sometimes they are so minute, so small, that it's only been discovered in the last few hundred years or so what these things are. But as science progresses, and it makes discovery after discovery, it really hasn't gotten around these wonderful things that the deeper you go, the more wonderful it gets, and the more mysterious, and the more amazing, and the more that you can see that it was intelligently designed from the very beginning. And so something like water, something as simple as H2O, is really something that I think a lot of us just take for granted. We turn on the tap and it comes out of the faucet, and we have ready access to this water. It is everywhere. It rains on the skies. We can go down to the beach and we can look out the ocean, the vast amounts of water that are there. But how often do we sit there and contemplate that our very lives are dependent upon this substance? And as we're going to see tonight, this substance called water seems to be designed for life, that it has that very purpose in its unique qualities among everything else. And so hopefully after the end of this talk, you'll never look at water the same again. So what we're going to do tonight is we're going to look first of all at the structure of water, as the boys are going to learn from Uncle Bob the H2O part of it and what makes water special. And we're going to do a little science kind of discussion here in chemistry. Not particularly my strong suit, but I did want to introduce to you a book that I've been leaning heavily upon. It's called The Wonder of Water. And this was written by a biologist named Michael Denton. And so we're kind of just doing a summary of a lot of the things that are found in this book. So if you're interested, you want to learn more and get deeper into it, I really suggest this book by Michael Denton, The Wonder of Water. And it was a conversation I heard with him one time that really piqued my interest on this subject, so I'm very thankful to be able to look into it a little bit deeper. So we're going to look at water itself, what it is. We're going to look at the unique properties of water, and we're going to be looking at particularly 5 distinct properties of water. And then we're going to see how important water is for our human bodies, for our living systems, our biological systems, how important water is for plants. We all know that to be true, but how does water actually work inside of a plant? And finally, we're going to look at water and our planet. The Earth is a very distinct planet, isn't it, by the amount of water that covers this planet. And we're going to look how these unique properties of water are so important for the ecosystem of our world. So let's start by talking about the chemistry behind all this. Now, what Uncle Bob did for those guys is he took them in his lab and he proved to them that water is actually made up of 2 elements or 2 atoms or 2 types of atoms, hydrogen and oxygen. Now, I haven't done chemistry in a long time, so I had to go to Roger and ask him a few questions about chemistry because that was his forte. And he gave me his old chemistry book. And I think it was written like 1727 or something. I remember saying. Maybe not that old, but here is Roger's chemistry book called The Textbook of Chemistry, and I was reading about water in this textbook. It was written sometime in the 1940s. But this line really caught my attention. It says, water itself has very unusual properties, perhaps ideal properties, almost as though designed for the role that it plays in the functioning of living matter. Almost as if, I'm going to say to you, I'm going to go out on a limb and say it's not almost. It definitely is once you get through all this and you realize this. But even those who don't believe in a God really see this as a remarkable property, this water. So if you take chemistry class, and anybody who's taking chemistry class will recognize this table. What's it called? The periodic table of the elements, right? Did you take chemistry, Mark? Yeah. He's looking pretty scared right now. And if you've never taken that before, chemistry is the study of the atoms that make up our world and how they interact with each other. And so this table represents all of the atoms, all of the elements in our world, the very basic components of nature. And they all go down to all these different elements. And they're grouped together in this table in a special way. But for our purposes, we're going to be looking at this top one here in the top left-hand corner, which is hydrogen. And then as you can read it from left to right, top to bottom, and as you go along, there's helium, lithium, barium, boron, carbon, nitrogen, and there's oxygen in our table. So water is made up of 2 of these atoms, these elements, and 2 of these, 1 of these, oxygen. So that's why we call it H2. There's 2 hydrogens and 1 oxygen atom. Now, atoms themselves are defined, and why they're in the table like this is they found out that atoms have what are called protons, they have neutrons, and they have electrons, right? Protons, neutrons, and electrons. And it's the number of those in the atom that define its characteristics of what it does and how it reacts with different things of that nature. So water is very special in how these 2 elements, hydrogen and oxygen, interact. So you can see in this graphic here, here's 2 hydrogen atoms. Now, a hydrogen atom is the most simplest of atoms. It only has 1 proton and 1 electron. And you can think of the proton in the middle. It's quite large. And you can think of this electron orbiting or spinning around that very fast, buzzing around it in this kind of cloud, or what they call it, like a shell. And then here's the oxygen atom, and it has 8 protons in the middle with 8 of these electrons buzzing around them. And what happens in water is that oxygen, it likes to share electrons. They call it like an electron hog. And so when hydrogen comes along in the right mix, it's created, it will basically grab these 2 hydrogens because it wants these 2 electrons, it wants to share these electrons, and they come together, these forces come together, and basically the hydrogen glues to the oxygen by these forces that are making them go together like this, and they share electrons. And so that's why they call them covalent electrons in the system. And so a water molecule, if you got really down to it and you were able to see this, you can't see it with your naked eye at all, but this is what water is. It is this molecule, H20. But what makes it really special is these forces inside of this atom, that draw them together, are electrically charged. So you'll see here there's a positive sign here and a negative sign here. And that when these draw together, it actually is more positive on one end and more negative on the other end. And so they become like a little magnet. That, you ever played with magnets before, and how one way they'll go and they'll click together, and you turn them around and you try to put them together and they'll repel each other. But little water molecules just have a little differential in their electric charge that is causing them to be attracted to one another. So you see the positive will be always drawn to the negative. And so this hydrogen side of the water molecule will be drawn to the negative side of another water molecule, and this is what they call the hydrogen bond. The hydrogen bond. And it's this hydrogen bond which bonds all of these water molecules together, all together. But it's a very weak kind of bond, so that these water molecules are always making and breaking these hydrogen bonds, and they're just kind of all just going around like this. And that's what creates this liquid of water. It's all these molecules dancing around each other, creating these hydrogen bonds. Now, if you put enough heat into it, all these hydrogen bonds are broken, and the water just kind of goes into a gas. It goes into a vapor. They all separate and go their own merry ways. But when they cool down again and they're attracted together, they condense together and they start forming water again. And then if you bring the temperature down, as we know in Canada, right? If you get cold enough to 0 degrees Celsius, all of those hydrogen bonds freeze into place and it becomes ice, right? So that's what water actually is, the basis of it. Now, when I say that's what water actually is, and I think a lot of chemists and physicists just sit there and go, well, that's what water is. We've seen, this is how we define water. But you think, well, why does it have to be this way? And chemists and physicists talk a lot about these forces. There's these forces inside of these atoms that are attracting and repelling one another. Well, what are these forces? What are these energies? What are these charges that are talked about? And then you have to go to another level and talk about quantum mechanics and quantum physics and all those kind of things. And even then, you're just talking about particles and things that draw one another to each other. So what defines that these two hydrogen modules will be at this exact angle, which is actually very important that they're at this angle of 140 degrees, makes them very strong, or what defines that this is creating a poles at either end? What's just the level of these forces and everything that draws it together? Why do they stick together? Why does an atom stick together? And why do they attract it to each other? Well, again, they talk about these protons and these electrons are kept together by what they call a strong nuclear force. It's a force that just keeps it. It's very strong at a very, very short distance, and it's keeping it all together. But if they're so strong right here, well, there's another force here. It's called the electromagnetic force. It's weaker than this strong nuclear force, but it goes over a longer distance. And that's what's attracting these. So basically what science has done is just put names to these kind of things. But when you look at it, why is it that way? It seems to be, as we're going to see, perfectly balanced in every way. This is a quote from a fellow named Fred Hoyle. He was a very famous scientist in the last century. He was an atheist, but he could not bring his brain around to think, how did life begin on Earth? He says, there's no way. So he believed that life came from outer space on meteors. But this is what he had to say, and it's a very famous quote. He says, and he's talking about the carbon atom. The carbon atom is another one of our elements in the table of elements. That's very important for life, extremely interesting atom. But I think he would say this the same for the water molecule. Would you not say to yourself, some super calculating intellect must have designed the properties of the carbon atom? Otherwise, the chance of my finding such an atom through the blind forces of nature would be utterly minuscule. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces we're speaking about in nature. So this is what he said, and of course, like I said, he was an atheist, but he can very well see the things that he studied in nature, that it's unexplainable. Why is it this way? It's like somebody actually set it up. Well, we believe somebody did. And so the physicists and the chemists get around these kind of things by just saying there are forces, there are charges, there are energies. But they're just putting names and numbers and formulas to these kind of things. I have a quote from another gentleman named David Berlinski, and I think he really puts this perfectly, and it's kind of like a little philosophical moment to think about this. But he says, the laws of nature by which nature is explained are not themselves a part of nature. No physical theory predicts their existence nor explains their power. They exist beyond space and time. They gain purchase by an act of the imagination and not observation. They are the tantalizing traces in matter of an intelligence that has so far hidden itself in symbols. David Berlinski is an agnostic. He doesn't know whether there's a God or not, but he can very well see in math, his specialty, that there are these symbols, that the universe that we live in is so beautifully defined by math, by numbers, and by formulas. And he just says it really does. It's tantalizing traces in matter of intelligence. And that's what the water molecule really is. So this proportion of the water molecule and how it's in that shape and how it has this plus and minus built into it and how it's attracted through hydrogen bonding is really on a razor's edge of perfection of what it needs to be for all life to be on this planet. And it gives it some very unique properties that you'll see in no other molecule on the planet. So let's go through these properties. There's 5 of them. It exists as a liquid and an ice and water. So we're all familiar with the 3 different phases that water exists in our planet. And that's quite unique. All other substances, like just take for example on this chart, there are other elements that will bond with hydrogen that will share covalent electrons. Telluride, selenide, sulfide, they'll all do the same kind of thing. But their freezing points and their boiling points are considerably different. Consider hydrogen telluride, which freezes at negative 49 degrees Celsius, and then it starts boiling at negative 4 Celsius. Well, water, we didn't even think about boiling at that. It's still in a frozen state. And so you look at all these other kind of elements, these other kind of molecules, and it just even gets worse. Hydrogen sulfide, its freezing point is negative 84, and its boiling point is negative 62. So we never see it as a liquid or as a solid. It's always in a gaseous state on our planet. But water, which is really, by these terms, hydrogen oxide, a very similar kind of component to these other ones, because of the way that it's set up by its energies and by its properties, it freezes at 0 degrees Celsius, and it boils at 100 degrees. So we're all familiar with that, right? We live with that. But that's a very, very unique property of water itself. You will not find that in any other type of liquid on the planet. Well, let me ask you this question. Does ice sink or does ice float? This is another unique property of water. Now, this wasn't always a case, an obvious case, because you know Galileo, the scientist. He lived back in the 1600s. He actually had a debate with somebody about how ice floats, because it wasn't always obvious. People are saying, yeah, when things get denser, when they freeze, they become heavier and they will sink. Everything else, when it condenses like that and freezes, sinks in its own liquid form, but not water. Ice actually floats. All Galileo really had to do was to push an ice cube down into water, let go of it, you'll see that ice cube float right back up to the top, right? Now, why is that? Well, water has this unique property because of its hydrogen bonding, that when it freezes, it actually stops that kind of like those weak hydrogen bonds. When it freezes, it actually forms a crystal. And the atoms become more spaced out from one another, and therefore it becomes less dense than in its liquid form. In fact, the water is the most dense at 4 degrees Celsius. So water, as it gets cooler, will start to go down, but as it gets past 4 degrees, it will start expanding again, and it will float to the top. That only happens with water. An interesting property. So you can see the power of that. We see it all the time in Canada, right? If you leave water in a pipe during the winter, what happens to the pipe? It bursts. The water is so powerful when it expands that it has the power to burst open a copper pipe. Water has a high heat capacity, and what I mean by that is that water, it takes a lot of energy, it takes a lot of heat into water to get it to heat up. So when you're boiling a pot of water on the stove, you're putting a lot of heat in there to get it to boil. Now, that's not really true of a lot of different substances in this world. Take, for instance, sand, which we've got up here, which is a silicon oxide. It has the way that they measure this, it's actually very much lower, 0.188. Now, practically, you see this if you go to the beach, right? As you get out of the car and you see the beach and you're going towards the water, you have to walk over the sand. And you're going, right? As you get over that hot sand, you can feel that its heat capacity, it absorbs that heat so well. And it gets really hot. But once you get to the water, you're like, right? Because that same sun is hitting the water, but it's not heating up as quick, right? It's absorbing the sun's energy into the water. Now that's very distinctive of water as well. This high heat capacity that's going to play a very important part. Water is sticky. You ever think of water as being sticky? It adheres to things. Now, I just need a drink of water. If you put your hand in water and you take it out, you have water on your hand, right? It's sticking to your hand. Therefore, it's adhering to your hand. It is sticky. And it has a special way of, on the surface of the water, this stickiness is on the surface. It's called surface tension. And so the surface of the water is stronger than in the middle of the water. So you ever seen those little water bugs that kind of go around the water? And they glide on the water? You wonder, why don't they sink? Well, they rely on this property of water called surface tension. And they're able to skittle along the top of the water and not sink. Or do you ever see dew or a water that's on a plant? Or maybe you just washed your car, a nicely waxed car, and the water all beads up on it, right? Well, that's this surface tension effect that it has, that this water is sticky. And so it has this tension to it that the water molecules are drawn to one another, yet it is very slippery in another way, right? Because you can pour this out, and it readily just pours out. That's called the viscosity of water, right? Or the viscosity of any sort of fluid is how well does it flow, basically. And water has a very low viscosity. It flows very well. It's not like oil. It's not like molasses, right? Those things the viscosity is very high, so they don't flow well. And so it has those unique properties as well. Its viscosity is very, very low. And then finally, water is what they like to call a universal solvent, or almost a universal solvent, is that almost everything dissolves in water. It's actually very amazing that way. So if you put a sugar cube in a glass of water, what happens to it? Well, it dissolves. It just disappears before your very eyes. But what happened to the sugar? Did it go away? If you take a drink of it, you realize that the sugar is still there. You can taste it. But what has happened is the water molecules, those hydrogen bonds again, those charges inside of there are overcoming the molecules in the sugar, and they're actually capturing them inside of the water molecules. And it works that way to disperse it throughout the water. So there is a reaction happening there. It's not a chemical reaction. It's just the interaction of these electrical forces that are there. And so a lot of these kind of different substances, do the same thing with salt or whatever it is, they will dissolve in water. They are what we call water friendly. Now there are things that won't dissolve in water. You know what they are, like oil, right? You pour oil into water and it just seems to coagulate in water. That's because it's electrically neutral. It has no charge to it. It's not attracted to water, so it repels it. So these are the 5 important things that as we go through how incredible water is, we're going to be referring back to these 5 properties. I want you to remember these. First of all, that water exists as liquid, ice, and vapor on our planet, on the ambient temperatures of our planet. And it's quite unique in that way. Ice is lighter than water. It gets less dense. It has a high heat capacity. Water is sticky yet slippery. It's viscous. And finally, it is a universal solvent. Now, I saw a website that actually listed 70 anomalies of water that made it unique. We've just come down to these 5 here that I wanted to share with you. So as we go through what makes water so important for life, it really depends on one of these properties or a combination of these properties working together. NASA, the space exploration government agency, they're trying very hard to find life on other planets. And their motto is, follow the water. And so they have rovers up on Mars right now. You can see it in the news every once in a while. And what are they looking for? They're looking for water. Now, they have found water on Mars, and it's mainly frozen in its poles. But it seems to have been covered by water at one time. So they're very busy looking for life. And I don't think that would really mean much to us if they found life on another planet. It would just mean that God's created life somewhere else. But when they're looking for water, they realize that life really can only be associated with water. And any other substance is inadequate. It will either break down water or break down life or be disastrous to life in any sense. Our human bodies have a lot of water. By certain counts, we have between 60 and 65% of our human bodies are made up of water. We're basically walking bags of sloshing water. But that water is really trapped inside of in our cells and in our blood. But you can see the list of all the things. I don't know how they really come at these numbers, but our brain is made up of 85% water. And as you go down the list, you get down to blood, which is 50% water. And then, of course, I'm really surprised to find teeth even have any water in them, 8 to 10% in our teeth. And it varies with our ages. Babies actually are about 80% water. And then as you get older and older, you lose more water, and it goes down from there. But as you can see here, water is very important for us, isn't it? You can't... how many days could you go without drinking water? You know, it's like 3 days or whatever that is. So it's very important for our systems to have water. We're very dependent upon it. And some of these very special properties of water are in the very parts of our cells around our DNA. They're interacting with the proteins that are there. Our bodies are taking this aspect of specific heat and using that to transfer the heat around our bodies. That thermal heat that's in our bodies that's being generated is being transferred to the outside of our bodies so that it might be taken out from there, right? We don't burn up. Our water is actually helping us to cool off. And we know that to be the fact because there's another amazing part of water that as it evaporates, as its heat lets loose, it actually cools in the process. And so that's why we sweat when we get hot, or maybe we perspire. And so built into our bodies is this heat transfer mechanism taking the water that's inside of us and cooling us off. It's very important for that aspect as well. But, you know, I wanted to focus on, there's tons of aspects about water in our bodies, but I wanted to focus on one particularly, and that's the blood in our bodies. And our blood is about 50 or 55% water. And as we talked about, water is kind of this universal solvent. It has this remarkable ability to dissolve things in it. And it becomes this remarkable carrier around our systems for our blood supplies. And so our body, of course, as you know, our heart is pumping through veins in our bodies this blood, which is bringing oxygen and nutrients to our system, based mainly on water. And by the solubility of all these nutrients and these blood cells in the water to carry them through our veins. Its viscosity is just right to do this. We talked about how it flows, right, so easily. If water was any thicker, it wouldn't be flowing through our veins the way that it should, and we would slowly be starved of oxygen. So it stands really in our bodies on a very special place. And anybody who designs hydraulic systems, who pumps water through pipes, realize how important the size of the pipe is according to water, because as it's pumped through, there is some friction going through there, and you have to design that properly in order to get water through a pipe. Our body, our blood system is beautifully designed according to these principles of water, the viscosity of water, and the pressures that it pumps through are capillaries. Now, the exchange of oxygen and nutrients happens through these very, very tiny blood vessels called capillaries. And this is where the exchange goes out of oxygen and nutrients into the body, and then the body puts back into their carbon dioxide and the waste to be carried out. But that is a very, very fine thing to put through there. But water is specifically designed very well to go through those small capillaries and carry all of those blood vessels and the nutrients that our bodies needed. And as the physicists and the doctors have gotten down to studying the blood system and all those kind of things, they can see that water seems to be specifically designed for this very purpose. So we have water, we are 60 to 65% water, and we have water basically coursing through our veins. So it is very much our life in our systems, but not just our life, it's also very important for plant life in a very different way. Now we know this, if we don't water our plants, they die, right? So how does a plant get water into its system? Well, it uses something called the capillary action of water. And we talked about how sticky water is, how it has this surface tension to it, how water really attracts water. I'm going to show you a little video that shows these things called capillary tubes. They're just very small tubes. And he has a solution here. He's just dyed it purple so that you can see it better, but really it's like water. And so he's going to grab a tube. Now watch what happens when, this is just a tube, it's just like a straw. Now when you put a straw in water, what happens? Does it go up the straw just all by itself? It doesn't, does it? But as he puts this straw in here, you see the water starts going up the capillary tube. This is called the capillary action of water. The positive and negative charges on the water is actually attracted to the sides of the tube, to the glass. And it keeps adhering to this. In fact, if you go home and you fill a glass with water, if you look very carefully at the edges, you'll see that the water, as it gets near the glass, will actually go up like this because it's attracted to the glass. And when you get small enough and smaller, that capillary action will actually draw the water up the tube, defying gravity. But this is actually the inner workings of the water being attracted to the inside of the glass tube. Now he's going to get one more, a little bit smaller here. This is the smallest one he has. It's 0.4 millimeters. So he puts it in the solution. I think he stirs it around here to break the surface tension. And you can see it'll start to go up the tube. Now the smaller the tube, the farther it goes up the tube. It's just the way the properties of water, again, working in this. Now, plants use this principle to draw water up through its whole system. So take, for instance, a tree. You could have the redwood trees that are hundreds of feet high. Yet at the very top, it's supplying water to its leaves or its pines. How does it do that? How does it get up there? Well, anybody knows a little bit about plant biology will say, well, it's the xylem. Oh yeah, the xylem. Well, the xylem are these little fine tubes that go from the roots of the plant through the stem or the trunk. All plants have this. And they go up through the stem or the trunk. And they go up to the leaves, these fine little tubes. Now, these tubes are anywhere from 0.03 to 0.3 millimeters. So they're even smaller than those little capillary tubes he was using right there. They're just a little bit bigger than your hairs on your head. That's how fine they are. So they're going to be able to draw up through this capillary action the water, taking advantage of the properties of water to draw it up through these tubes. Plants are ingenious, aren't they? Or were they created this way? So this is the roots. You can see the water going in through the roots. coming up these xylem, these very thin little pipes coming up the trunk of the tree, up into the leaves where the water is going to be used. That doesn't get us all the way, though. Capillary action really seems to be a big part of how trees get their water up a part way, but they also depend on this little part of the leaf here called the stoma. And in the stoma, there's something that's going on called transpiration. It's like evaporation. When a water molecule breaks free and evaporates into a vapor, it actually is creating here, by design, it's creating a negative pressure on this part of the leaf. So it evaporates, and that evaporation actually cools the leaf, and it creates a negative pressure. Now, the way that water acts, and with the tension and the way that they're drawn towards each other, this negative pressure will draw all of the water up the whole tree, up into the leaves. And the more sunlight you get, the more transpiration you get, and the more the water gets brought up into the leaves of the tree. When it cools down, it will regulate itself and go back down again. So this is the pumping system of plants and how they get the water up through their whole systems by using these very special properties of water that are capillary action. It's basically this aspect that water is sticky, and it has a high tensile strength because of that. In his book, Stephen Vogel, in a book called The Life of a Leaf, he says the pumping system has no moving parts. It costs the plant no metabolic energy. It moves more water than all circulatory systems of animals combined, and it does so against far higher resistance and depends on a mechanism with no close analogy in human technology. And it is simply amazing that it's using the properties of water to deliver water where it needs water. It's absolutely incredible how it does that. Now, why do plants need water? Well, it's all because of photosynthesis. And the plants are making their food. What they need to make food is water and carbon dioxide. And there's this process happening in the leaves called photosynthesis, which is creating the food for the plant. And in photosynthesis, you need sunlight, because it's using the properties of sunlight and the visible spectrum of light in what's called the chlorophyll of the plant to take carbon dioxide, which is everywhere in the air, in which, remarkably, we as humans actually breathe out. It's waste to us. We just breathe it out. But the plants take it in, plus the water that they're soaking up through the xylem into the leaves. When these two combine, the sun's energy is causing a chemical reaction between these two so that you get carbon, hydrogen, oxygen combination, which is a sugar, which is the food that the plant is using, plus you get a little oxygen left over, 2 oxygen. Now the plant doesn't need this oxygen, so what does it do with it? Boots it out of the plant, doesn't need it. Puts it out in the atmosphere. Well, this is what we breathe. We need that oxygen. So we breathe in the oxygen, and we have a similar reverse process inside of our cells, which takes that oxygen, combines it to make for our metabolic energy purposes, and spews out carbon dioxide. Now you talk about a system that has some foresight behind it. That we have this kind of symbiosis in our systems, in our world. That's plants, and that's their dependence on water. And the third part is even more amazing. Because, as we talk about water in our bodies and in plants, and we talked about how in our bodies we're made about 60% water. Well, when you look at our planet, the ocean extends over about 70% of the Earth's surface. It's a very similar type of ratio. And water in itself is like a circulatory system on the planet Earth, which makes our earth really a living system. And it's water that does that. And it's the unique properties of water that does that. And you think about all the water that this planet has. The deepest ocean is found in the trenches where the plates are subducted. The Marianas Trench is 11,035 meters deep. That's higher than Mount Everest is high. And so men have rarely been able to go to those depths. It's quite impossible, almost unheard of, for men to go to those depths by themselves. It's easier for them to go to Mount Everest or to the moon than to go to the depths of the ocean. So how much water is there on the earth? You know, if all the solid earth, if you took all the mountains and everything and you just flattened everything, the seawater would cover the entire earth to a depth of 2,440 meters. That's 1.5 miles high. We'd all be under 1.5 miles of water. If all the water vapor in the atmosphere were converted to liquid, it would cover the smooth earth by 1 inch. So you see, there's not just a lot of water in oceans and lakes and rivers. There's a lot of water in our atmosphere as well as a vapor. And that's very important as well. So there's a lot of water, and you look at the other planets like Mars and those kind of things, you don't see a lot of water like this. Where did all this water come from? Where did it begin? You know, that's a real kind of mystery for scientists who thinking about the origins of the planet. And they have some theories. They say maybe it was just there in the rocks, and as the molten rocks cooled, the water just kind of came out like a sponge. Or maybe the water on our planet came from comets. You know, comets are made of ice, and maybe billions of years ago our planet got hit by a bunch of comets, and the water in those comets melted on our Earth. You know, there's no proof of all that. But you know, it's interesting from a biblical perspective, it's kind of the same. Water's always been there. The oceans have always been there. And the scientists will tell you, it looks like the oceans have always been there. It looks like the volume of water on the earth has always been there. In Genesis 1, verse 2, it just says, and the Spirit of God moved on the face of the waters. So even in Genesis, it's not part of the 7 days of creation. It's just there, the oceans. And they're such an important part to our planet. The oceans are all connected. And so this heat capacity of water is like a buffer for our Earth to maintain a constant good temperature for us. If the oceans weren't there, if we weren't so covered with water, you wouldn't have kind of the stability of the planet that we have. We would be constantly living in an ice age here in Toronto for sure if we didn't have this. But the water is constantly moving. It's being warmed up on the surface and blown by the winds, and those winds are blowing up the northern quarters where it gets cooled, and then as it cools, it gets heavier and it sinks, and it goes down to the bottom, and it comes the currents that flow down below. And these currents all flow around the earth. You know, in 1992, there was a cargo ship going across the Pacific Ocean full of bath toys, rubber duckies. And it got caught in a storm, and it sank. And all the bath toys floated to the top. There was 28,000 of them, and they just started flowing. And they found these bath toys all over the world. And that's the marvel of this system, these currents that go around our planet. And it's very important for our climate that these oceans are here and that they are cycling like they are. There's a lot of dependency upon these things for us and for the ecosystems of the fish and the water. And it's these churning of these kind of things that's very important, because we see that ice freezes. We have glaciers. But what are they doing? They're floating on top of the water. This is, again, another unique property of water, that it floats when it becomes ice. Imagine what would happen if that didn't happen. You would have ice sinking to the bottom of Lake Ontario year after year. It would never melt. It would just start to accumulate, to the point where maybe every summer you just have this big block of ice out on Lake Ontario. Maybe the top would start to melt or something like that. No fish, no aquatic life would ever live through anything like that. But because of the unique properties of ice to float, fish are actually protected under the layers of ice. They're insulated from being frozen to death because of the unique properties of water. And finally, we have the water cycle itself. Another amazing part of everything that happens is this water cycle. Where does rain come from? Well, it comes from clouds. Where does clouds come from? Well, the clouds come from the evaporation of the oceans. So it's said that every year the sun will evaporate off the oceans 3 feet of the oceans, off the water, into our atmosphere. That water, those water molecules going up into the atmosphere, will condense into clouds. When they get condensed enough, the water will come down on our planet and provide fresh water for us to live by. It'll run down the rivers into the lakes and streams. It'll go down into the ground as groundwater where we can tap into that with wells. So the water cycle is always cycling. It's a circulatory system, a living system for us as humans and for plants to be able to have water so that we might live. So it's the very properties of water that are causing water to be delivered for us to live. It's quite amazing. But that's not it. That's not the whole story either. Because as the water is coming down on the mountains and on the rocks, it's being frozen in there, and as it expands when it's frozen, it's breaking those rocks into pieces. And the water, because it likes to pick up things and carry them along because of its universal solvent, will pick up all these minerals and start bringing them down the rivers and streams to the plants that need them. And so there's all these aspects of water that we see in its unique properties that make that happen too. So if you look at the water cycle is dependent on water's unique ability to exist in 3 material states on Earth. That ability brings us water for terrestrial life here on Earth, but the erosion and weathering of rocks is dependent on several unique properties of water as well, which brings us minerals for life, and it also creates the soil needed for plants. And soil is an amazing thing, right? Because you think, well, the water's seeping into the soil, but when you water something, water goes into the soil and it sticks to the soil. So that cohesion, that stickiness of the soil, its very properties are there for plants as well, so that it can stick around for a while, and the water can be soaked into the roots of the plant. So we have terrestrial plant and animal life as well. So as you can see, there's several remarkable properties of water. 5 distinct properties that are all based upon this structure that water has, these energy states that are in there. And as we can kind of consider all of what water is, it really does speak of intelligent design. It really screams to us that there is a designer who has created these things, that it's perfectly balanced in so many ways. It is really very, very wonderful. And so I thought I'd leave the last word to Uncle Bob. We'll go back to his fix-it shop, and he'll close out the talk for us tonight.
Salt water is a very remarkable liquid. All life depends on it. And you know, water is a wonderful example of the Creator's great wisdom and careful planning.
I never thought about water that way before. Neither did I. I just drank it and forgot it.
Yes. I guess most of us never stop to realize what God has done for us by giving us water. We don't appreciate how much this common, ordinary substance means to us. We're so used to it, we just take it for granted. But it helps grow the food we eat. It provides electricity and steam for power. We use it to keep things clean. We boil things in it to sterilize them and prevent disease. We drink it. We skate on it. And we swim in it. We make snowballs out of it. We use it for cooking. And we keep things cold with it. Yes, water is essential to all life. Without it, there would be no grass, or trees, or any living thing. For without water, you and I wouldn't be alive right now. You know, it makes a person feel very, very grateful for water. Two colorless, tasteless, odorless, invisible gases combined in just exactly the right way to give us this wonderful, life-giving liquid. Just plain old H2O.